In this video, we're going to look at permutations, or counting and permutations, as it's called on your study click list. So May's team play a match, they can win, draw or lose. So there's 3 outcomes. If they play 2 matches, there's 9 outcomes. If they play the 3rd match, there would be 27 different outcomes possible. Hard to believe, but there are. So we are asked to fill in the table. They could win, they could win, draw, or they could win, lose. They could draw, win, draw, draw, or draw, lose, or they could lose, win, they could lose, draw, or they could lose, lose. May thinks that each outcome on the table is equally likely. Based on this, find the probability that when May's team play 2 matches, they win at least 1 match. So let's circle at least 1 match. Okay, they've won 2, they won 1, they won 1. They've just won 1 on this row, and they've just won 1 on this row. So the probability they win at least 1 match would be 5 over the total, which is 9. May's team play 5 matches in a competition. Work out the total number of different possible outcomes for these 5 matches. So there's 3 to the power of 5 here would be the simple answer. Or 3 by 3 by 3. 3 in each we saw. 27 for 3, then 81, 81 by 3, 3 to the power of 5, 243 will be the amount of different outcomes in 5 matches. A very similar question was asked in 2018. Hager takes part in a chess competition, and in each game she can win, draw or lose again. In each game she plays, each of these 3 outcomes is equally likely. Write down the probability that Hager wins her first game. And then in part B, fill out the table to show the 9 possible outcomes for the first 2 games. We've done this in the last question. Win, 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 draw. This is winning the first game. Win, loss. Then we have draw, win. These are all draw begins. Draw, 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 loss. And then these are all losses to begin with. Loss, win, loss, draw, loss, loss. So to win the first game, you can see there's 3 of them out of a total of 9. You could simplify to 1 over 3 if you would like. Part B we've done, and prime the probability. Wins game 1 and loses game 2. Well, there's only one possibility of that. Wins game 1 and loses game 2 is 1 win-loss, 1 over 9. And wins at least 1 of the first 2 games. You can see very similar questions get asked all the time. At least 1 of the first 2 games. Well, these are all wins, at least 1. This is a win, and this is a win as well. So there's 5 of them out of a total of 9 again. You can see the same as the last question. Again, following on with that trend, Hager plays 3 games, so there's 3 outcomes. We've seen this already, 3 outcomes and 3 outcomes, or 3 to the power of 3. There are 27 different outcomes for her first 3 games. And the probability she doesn't win any of her first 3 games, so that will be loss, 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 if she doesn't win any of her first 3 games. So that's 1 probability out of a total of 27. But we'd also have to include the draws. We could have draw, draw, draw. That wouldn't be winning any of our first 3 games. So it's a combination of when we don't have a W. So if we look at loss, win, draw. This has a W in it, so it doesn't count. So let's try and list them. We go LLL, LLD, LDL, and LDD. These are all the 4 beginning with L. And we could swap the letters around and we'd have plus another 4 that begin with D. Let's have a look at them. DDD, DDL, DLD, and DLL will be the other 4. So there's 8 probabilities of not winning any. I misread it to be thinking it was just to lose them all, but they're not the same thing. So there's 8 probabilities out of a total of 27 for part 3. Third example, a similar type of table, a 2-way table, but this time it's Junas has an unlimited supply of €5 and €2 notes. No such thing as €2 note, €2 coins. Fill in the table below. to show 3 different ways which he can use to make 27, and one is already done. So we just have to think maybe carefully about this. What about 5 5s or 25? That jumps out. 5 5 notes would be €25. We need €1, €2 coin, so that's a 1 and a 5. If you think about it, if we had 4 €5 notes, that'd be 20. We couldn't make up to 7, so we can't have an even number, it looks like. Let's try 2 just to eliminate that one. That will be €10. We'd need 17, which we can't make with €2 coins, so it looks like we have to have an odd number of €5 notes. 3 is the next one. 135, there'll be a pattern. That would be 15, which would leave 12, which would be 6 €2 coins. So a bit of trial and error. Jot stuff down always, and that should get you to the answer. Now in part B, we have to explain how he could use his supply of €5 notes and €2 coins to make every whole number greater than 3. I.e., and they give you this pretty much to confuse you, make n euros for every n is an element of natural numbers where n is greater than 3. So he has to be able to make 4, which is divisible by 2. So therefore yes. And 6 will be divisible by 2. Therefore yes. So every even number, we would write down every even number can be made with just €2 coins. Jot that down, €2 coins. Euro symbol. So we've covered, I'll just jot them off to the side. We've covered not 2 with every number greater than 3. So we're looking at 4, 6, well 5 is in between. We can definitely cover that. 7 is 5 plus 2. So we've covered that. 8 we have covered. 9, the next odd number, would be 5 plus 2 plus 2. So you can see that that pattern will continue. We'll be able to make every single number after 3. In this question, instead of a two-way table, we're just given a list here. It's a 3-course dinner made up of a starter, a main course, and a dessert. How many options have we got? We've 4 starters, 5 mains, and 3 desserts. So the number of different outcomes is 4 by 5 by 3. The fundamental principle of counting. 20 by 3 is 60 different dinners. 60 different dinners can be had here. Then in a restaurant, there's a circular poster for each course where the options are presented or are represented by sectors of equal area. The poster for starter is shown. You can see all these are right angles. 360 divided by the number. So 360 over 4 is 90 for the starters. Calculate the angle in each sector of the mains. Okay, well that's 360 over 5, which is, that's going to give 72, 350 and 10, 72 degrees. So okay, you'll be using your protractor here in part 3. And desserts will be 360 over 3, which will be 120 degrees. So kind of combination of constructions here with a little bit of probability. You're asked then to draw them. Let's have a look. So here's where you're asked to draw them. And the 120 is kind of an easy enough one to draw. It's the C and D symbol, if you guys know that. These should all be 120 degrees. You see this peace symbol on the football pitch at the moment in Italy. In the center circle, peace in Ukraine. And then the 72 degrees, I'll leave that to you to take out your protractors and calculate 72 degrees. The best way to do it is just pick one straight line going directly up and then measure your 72. Less than 90 should go to about there. Mark in the 72 degrees all the way around. Just keep measuring them. Now part C, the owner of the restaurant wants to increase the number of different 3-course dinners that can be ordered. She's either going to add 1 starter, 1 main or 1 dessert to the menu. Which should she add to make the different number of possible 3-course dinners? So let's just remind ourselves how many of each there were. So there were 60, 4 by 5 by 3. Well, what about if we add a starter? It's 5 by 5 by 3. Just write down, this is if you add a starter, 25 trees, we'd have 75 dinners or different dinners. If we add a main, it would be 4 by 6 by 3. This is if we add a main. 24 trees or 72. And if we add a dessert, it will be, put the D down, 4 by 5 by 4, which would be 80. 20 by 4, 80 different dinners. So to get the most amount of different dinners or 3-course meals, she would add a dessert, and your reasoning is the maths behind the answer. In this question, it could easily be meals, starters, mains, desserts, and aperitivos, but in this case it's John going to a festival. Instead of food, it's just clothes. Examples of 2 different outfits John could select to wear. Well, he could wear black jeans. This is what they're looking for here. Black jeans, white shirt. Seems silly, but you know the maths behind this. Black jumper and 3 pairs of shoes, boots, sandals. Let's give him flip-flops because he's going to a gig. It's going to be mucky. And then just write a second one down as well. How many different outfits can he wear? 3 by 4 by 2 by 3, the fundamental principle of counting. 12 by 6. He has 72 outfits to wear at the concert. So you can see the same maths in all of these questions. Following that trend of clothes, we have a football strip containing a shirt, shorts and socks. Aspen United have 2 shirts, blue and green. They can also select from 3 different colours of shorts and 5 different colours of socks. I'm just going to underline the numbers. 2 by 3 by 5 is 6 by 5, so they have 30 different strips. Willow Celtic play in an all red strip. When Aspen play Willow, Aspen are not allowed to use their red shorts and their red socks. So we've 1 less on the shorts and socks. We still have 2 shirts, we now have 2 shorts instead of 3, and we have 4 socks instead of 5. 4 by 4, they've only got 16 outfits that they can wear. So really straightforward permutations questions.